Galaxies defy your expectations about cosmic shapes. Most people imagine round balls of stars floating in space. Gravity alone should create spheres, but something else intervenes. Tonight we're discovering the cosmic force that flattens entire star cities. You'll see how rotation creates the thinnest structures in the universe, and why almost every galaxy becomes a spinning pancake. Before we dive into these cosmic carousels, drop a comment about what you think shapes the universe. If you enjoy these space revelations, consider subscribing. These explorations are meant to be shared. Every clear night you see proof staring back at you. That pale band crossing the sky isn't random starlight. Ancient people called it the Milky Way without knowing what they were really seeing. You're looking at our galaxy from the inside. Edge on. That band stretches completely around Earth because we live within an impossibly flat disk. The view proves our location, embedded inside one of the universe's thinnest structures. Astronomers measured this disk's proportions. Our galaxy spans 100,000 light-years from edge to edge. Its thickness, just 1,000 light-years. This creates a ratio thinner than paper compared to a dinner plate. When you see the Milky Way tonight, you're witnessing galactic architecture from the ultimate inside perspective. For centuries, the Andromeda Galaxy appeared as a fuzzy smudge in telescopes. Astronomers couldn't determine its true nature. Some thought it was a nearby gas cloud within our own galaxy. Photography changed everything. When astronomers captured long-exposure images, Andromeda's real structure emerged. The galaxy appeared edge-on as a razor-thin line, absolutely flat. Astronomers realized they were seeing another massive star city, viewed sideways from an enormous distance. This discovery revealed the universal pattern. Galaxy after galaxy displayed the same extreme flattening. 2.5 million light-years away, Andromeda confirmed that cosmic disk architecture dominates the universe. Every major galaxy we observe shares this pancake geometry. Astronomers classify galaxies into distinct types based on their shapes. The overwhelming majority fall into one category: spiral galaxies. These cosmic cities all share the same basic architecture. Each spiral galaxy contains a flat disk with curved arms. A central bulge sits at the core like a cosmic egg yolk. The arms wind outward through the surrounding pancake structure. This pattern repeats throughout the observable universe. Hubble Space Telescope surveys reveal billions of spiral galaxies. Each one displays the characteristic disk and bulge design. Scientists estimate that 70% of all large galaxies follow this flat architecture. The universe's preferred method for building massive star cities is the rotating disk. Round galaxies exist but remain the cosmic minority. Stars don't spread evenly throughout galaxies. Detailed surveys reveal where stellar populations actually concentrate within these cosmic structures. Mapping projects count individual stars across galactic regions. The results shock astronomers. Stars cluster overwhelmingly within the thin disk plane. Above and below this disk, stellar density plummets dramatically. Within just a few thousand light-years of the galactic midplane, star populations drop to nearly zero. The vast majority of stellar residents lie compressed into this impossibly thin layer. Three-dimensional mapping confirms this extreme concentration. 99% of all stars occupy the disk region. The remaining galactic volume stays essentially empty of stellar populations. This distribution proves that disk formation concentrates stellar material into the universe's flattest neighborhoods. Common sense suggests that galaxy disks rotate like solid wheels. If this were true, Stars at the edge would move much faster than those near the center, just like points on a spinning record. Astronomers measured actual stellar velocities across galactic disks. What they discovered defied expectations completely. Stars throughout the disk maintain surprisingly similar speeds regardless of their distance from the center. This creates what scientists call differential rotation, different regions spinning at carefully coordinated rates. Our galaxy demonstrates this pattern perfectly. Stars in the outer regions cruise at 200 kilometers per second. Inner regions move at nearly identical velocities. One complete galactic orbit takes our solar system 200 million years. This synchronized spinning motion maintains the disk structure while preventing gravitational collapse or centrifugal breakup. Galaxy disks achieve proportions that seem physically impossible. Their extreme thinness challenges our understanding of how massive objects can maintain such delicate geometries. Comparison reveals the shocking scale. If you shrunk our galaxy to the size of a large pizza, its thickness would measure less than a sheet of paper. This represents one of the most extreme aspect ratios found anywhere in nature. Other cosmic structures pale in comparison. Planets, stars, and even planetary rings appear thick and bulky next to galaxy disks. Only the thinnest soap bubbles approach similar proportional extremes. Despite their delicate appearance, these structures contain hundreds of billions of stars. The gravitational forces involved dwarf anything experienced in our solar system. Yet somehow, rotation maintains this knife-edge balance between collapse and dissolution across cosmic timescales. Galaxy disks don't maintain uniform density throughout their extent. Stellar and gas concentrations follow specific patterns that reveal the underlying physics of disk formation. Central regions contain the highest stellar densities. Moving outward from galactic cores, star counts drop steadily but follow predictable mathematical curves. This creates what astronomers call exponential decline profiles. The pattern holds across galaxy types and sizes. Massive spiral galaxies and smaller disk systems both show similar radial distributions. Matter concentration peaks at the center and falls off systematically toward the edges. This distribution results from the balance between gravitational attraction and rotational support. Central regions collect material most efficiently. Outer zones spread matter more thinly but maintain structural stability through orbital motion. Understanding these density patterns helps astronomers model how disk galaxies form and evolve over cosmic time. Spiral arms create the most recognizable features in disk galaxies. These curved structures win through galactic disks, creating the iconic patterns visible in astronomical photographs. Logic suggests these arms should quickly wind up and disappear. If arms were simply rotating with the stellar material, differential rotation would wrap them into tight spirals within just a few rotations. Instead, spiral patterns persist for billions of years. Our galaxy has maintained its spiral structure throughout most of cosmic history. The arms continue to exist despite countless galactic rotations. Scientists now understand that spiral arms represent waves of density moving through the disk material. Stars and gas flow into these density peaks, become compressed, and then flow out again. The wave pattern itself rotates at a different speed than the individual stellar orbits. This creates a cosmic traffic jam that maintains the spiral appearance while individual stars continuously cycle through the arm regions. Within galaxy disks lies an even thinner layer that challenges our concepts of cosmic architecture, the interstellar medium, gas and dust between the stars, occupies a region far flatter than the stellar disk itself. Astronomers mapping gas distributions discovered this ultra-thin component. While stars spread across roughly 1,000 light-years of disk thickness, the gas layer measures just a few hundred light-years thick. This creates a disk within a disk. The gas forms an incredibly thin sheet embedded within the already flat stellar distribution. Radio telescopes reveal this component as the thinnest large-scale structure known in the universe. Cold gas remains confined to this narrow layer through a balance of forces. Stellar winds and supernova explosions heat and stir the medium. Gravity and magnetic fields constrain its vertical extent. The result is a cosmic creep filling the galactic pancake. New star formation occurs almost exclusively within this ultra-thin gas layer. Visible stars and gas represent only a small fraction of galactic mass. Surrounding every disk galaxy lies a massive, invisible component that provides the gravitational foundation for disk formation. This dark matter halo extends far beyond the visible galaxy boundaries. Spherical rather than flat, it provides the gravitational well within which the disk forms and evolves. Computer simulations reveal how this works. Dark matter collapses first, creating the basic framework. Normal matter then falls into this gravitational well, but its ability to radiate energy allows it to settle into the thin disk configuration. The halo's spherical shape explains why disk galaxies can maintain their flat structure. The surrounding dark matter provides gravitational support from all directions while allowing the visible matter to find its most stable configuration: the rotating disk. Without this invisible foundation, disk galaxies could never form or persist across cosmic time. Something remarkable happens when spinning objects shrink. The faster they spin, the more they resist changing their rotation. This principle governs everything from figure skaters to forming galaxies. Scientists call this angular momentum conservation. It's one of the most fundamental laws in physics. Picture a figure skater spinning with arms outstretched. When she pulls her arms inward, her rotation speeds up dramatically. She's not adding energy, she's concentrating the same spinning motion into a smaller space. Gas clouds and space follow identical physics. As gravity pulls the cloud inward, any initial rotation becomes amplified. A slowly rotating cloud becomes a rapidly spinning disk. The mathematics are inescapable. When radius decreases, rotational velocity must increase to conserve angular momentum. This law shapes cosmic architecture throughout the universe. Gravity pulls equally inward from all directions, but rotation creates an outward force that opposes gravitational collapse. This opposition doesn't work the same way in all directions. Along the rotation axis, the invisible line through the center, gravity faces no opposition. Material collapses freely toward the center. Nothing prevents this inward motion. But perpendicular to the rotation axis, everything changes. Here, centrifugal force pushes outward with tremendous power. The faster the rotation, the stronger this outward push becomes. This creates a cosmic tug of war. Gravity wins along one axis. Rotation wins along the perpendicular plane. The result is inevitable. Matter collapses in one direction while spreading out in another. The compromise produces a flat disk where opposing forces reach perfect balance. Initial rotation in gas clouds appears almost negligible. The clouds drift and tumble so slowly that rotation seems irrelevant to their future evolution. Gravitational collapse changes everything. As the cloud shrinks, even tiny initial rotation becomes dramatically amplified through angular momentum conservation. Consider the scale of this transformation. A cloud initially rotating once every million years might end up spinning once every few hundred years after collapse. The same physical rotation gets concentrated into a much smaller space. Our solar system demonstrates this principle perfectly. The original solar nebula rotated very slowly. As it collapsed and formed the Sun and planets, that rotation accelerated enormously. Today, our entire planetary system reflects this ancient spinning amplification. Small beginnings create dramatic consequences when angular momentum conservation takes control. Two cosmic forces battle for control during galaxy formation. Gravity wants to crush everything into the smallest possible space. Centrifugal force wants to fling material outward into empty space. Neither force can achieve complete victory. Gravity alone would create spherical collapse. Centrifugal force alone would disperse the material entirely. Instead, these forces reach a delicate compromise. Along the rotation axis, gravity dominates and matter collapses inward. In the rotation plane, centrifugal force provides enough resistance to prevent further collapse. This balance point determines the final disk structure. Too little rotation produces thick, bulky disks. Too much rotation prevents any disk formation at all. The universe's flat galaxies exist precisely because most gas clouds begin with just the right amount of initial rotation to achieve this perfect balance. Different directions experience different collapse timescales during disk formation. This timing difference explains why flat structures emerge so efficiently from round gas clouds. Vertical collapse, along the rotation axis, happens rapidly. Without centrifugal force resistance, gravity compresses material quickly in this direction. The process completes in just a few million years. Horizontal collapse proceeds much more slowly. Centrifugal force increasingly resists further compression as rotation speeds up. This creates a gradual settling process that can take hundreds of millions of years. The result is asymmetric evolution. The cloud flattens quickly in one direction while maintaining its width in the perpendicular plane. This timing difference automatically produces the thin disk geometry. By the time horizontal settling completes, the vertical collapse has already created the flat architecture that defines galactic disks. On Earth, spinning objects eventually slow down due to friction with air and surfaces. In space, this energy loss mechanism doesn't exist. The vacuum of space provides a completely frictionless environment. Spinning objects continue rotating indefinitely unless acted upon by external forces. This preservation of rotation explains why galactic disks maintain their structure across cosmic time. Once formed, the spinning motion that created the disk architecture persists for billions of years. Our galaxy has been rotating for roughly 10 billion years. During this entire period, the basic disk structure has remained stable because space provides no mechanism for rotational energy loss. The universe's vacuum environment makes disk galaxies possible by preserving the angular momentum that shaped them during formation. Angular momentum changes only when external torques act on rotating systems. In the isolated environment of space, these external twisting forces rarely occur. Galaxy formation takes place in regions where neighboring massive objects lie at enormous distances. This isolation prevents external gravitational torques from disrupting the rotation. Without external interference, the spinning gas cloud maintains its rotational motion throughout the collapse process. The angular momentum present at the beginning remains constant until the final disk emerges. This stability requirement explains why disk formation succeeds so consistently. The universe provides the perfect laboratory conditions. Isolated, frictionless environments where rotation can proceed undisturbed. Only when galaxies later encounter each other do external torques become significant enough to alter or destroy the disk architecture. The original rotation in galactic precursor clouds appears almost trivial. These massive gas clouds rotate so slowly that billions of years pass before completing a single turn. Collapse amplifies this rotation beyond recognition. As the cloud shrinks by factors of thousands, the rotation rate increases by the same factor. What began as imperceptible motion becomes the dominant force shaping the final structure. This amplification explains why virtually all large galaxies display disk architecture. Even the smallest initial rotation, when amplified through collapse, becomes sufficient to create flat structures. Computer simulations confirm this process. Models starting with barely detectable rotation consistently produce thin disk galaxies after simulated collapse. The universe's disk galaxies represent the inevitable outcome of angular momentum conservation during gravitational collapse. Successful disk formation requires achieving precise equilibrium between competing forces. Too much initial rotation prevents collapse entirely. Too little rotation produces bulky, spherical structures. The balance point lies within a narrow range of initial conditions. Gas clouds must begin with enough rotation to prevent spherical collapse, but not enough to overcome gravity completely. Our galaxy achieved this perfect balance. The rotation rate allows material to settle into a thin disk while maintaining enough gravitational binding to prevent dispersal. This equilibrium state, once achieved, remains stable for cosmic ages. The balanced forces create a self-maintaining system where the disk structure persists indefinitely. Most observed galaxies demonstrate successful achievement of this critical balance point during their formation epochs. Angular momentum conservation operates identically throughout the universe. The same physics that flatten pizza dough shapes galactic architecture across cosmic space. From forming solar systems to massive galaxy clusters, spinning matter follows the same fundamental rules. Initial rotation plus gravitational collapse equals flattened structures. This universality explains why disk galaxies dominate the cosmic landscape. The physical laws governing rotation and gravity work the same way everywhere in space and time. Observations confirm this pattern. Distant galaxies formed billions of years ago show the same disk architecture as nearby modern galaxies. The physics of angular momentum conservation transcends location and epoch. Every spinning structure in the universe bears witness to this fundamental law that transforms spherical clouds into cosmic pancakes. The disk formation process culminates when all forces achieve lasting equilibrium. Gravity balances centrifugal force. Vertical collapse stops. Horizontal expansion ceases. This equilibrium state represents the universe's solution to the competing demands of rotation and gravitational attraction. The final disk architecture satisfies both requirements simultaneously. Once established, this balance becomes remarkably stable. The disk can persist for billions of years without significant change. Minor perturbations get absorbed without destroying the overall structure. Our galaxy reached this equilibrium state roughly 10 billion years ago. Since then, the basic disk architecture has remained constant despite ongoing star formation and minor gravitational disturbances. The universe's flat galaxies represent successful examples of this final equilibrium. Cosmic structures that found the perfect compromise between competing forces and achieved lasting stability. The early universe wasn't perfectly smooth. Tiny density variations existed, regions slightly denser than their surroundings. These seemingly insignificant bumps would become the birthplaces of every galaxy we see today. Dark matter clumped first in these dense regions. This invisible material responds only to gravity, so it began collapsing immediately when density reached critical thresholds. Dark matter halos formed the cosmic scaffolding. These massive, invisible structures created gravitational wells that trapped ordinary matter. Gas clouds fell into these wells and began the long journey toward becoming galaxies. The process started roughly 13 billion years ago. Those tiny early fluctuations grew into the largest structures in the universe through pure gravitational attraction. Every galaxy, including our own Milky Way, traces its origin back to these primordial density seeds planted in the cosmic dawn. Gas clouds face a fundamental choice during collapse. They can either form round, bulky structures or flatten into thin disks. The deciding factor is rotation. Scientists call the critical transition point gene's instability. This marks the moment when gravitational attraction overcomes gas pressure and collapse begins. Clouds without rotation collapse inward equally from all directions. Gravity pulls materials straight toward the center, creating spherical structures. This can produce what astronomers call elliptical galaxies, round balls of stars. But rotating clouds behave completely differently. Angular momentum prevents spherical collapse. Instead, these clouds flatten into disks as they shrink. The rotation axis stays short while the perpendicular plane spreads wide. This single factor, the presence or absence of initial rotation, determines the final architecture of cosmic structures throughout the universe. Gravitational collapse doesn't happen instantly. The process follows precise timing rules determined by the initial density of gas clouds. Dense regions collapse faster than sparse ones, a cloud's freefall time. The duration required for complete gravitational collapse depends entirely on its starting density. The mathematics are straightforward. Double the density, and free fall time decreases by roughly 30%. This relationship holds throughout the universe regardless of cloud size or composition. Our galaxy's collapse took approximately 1 billion years from start to finish. Less dense regions required longer periods, while the densest areas formed galaxies much more quickly. This timing sequence explains why different galactic neighborhoods show different ages and evolutionary stages across the observable universe. Collapsing gas clouds can't shrink forever. Eventually, they must reach equilibrium or risk complete dispersal back into space. The virial theorem describes this balance point. It requires that gravitational potential energy and kinetic motion energy reach specific proportions for stable structures. When clouds collapse, gravitational energy converts to heat and motion. This process continues until the internal energy becomes sufficient to resist further compression. The cloud reaches virial equilibrium. This balance point determines the final size and structure of forming galaxies. Too much kinetic energy disperses the cloud entirely. Too little allows continued collapse into black holes. Successful galaxy formation requires achieving this delicate equilibrium between gravitational binding and internal support mechanisms. Rotating clouds encounter an invisible wall during collapse. This barrier appears when rotation energy becomes comparable to gravitational binding energy. The angular momentum barrier marks the point where centrifugal force equals gravitational attraction. Further collapse becomes impossible without removing angular momentum from the system. Material piles up at this barrier, forming the thick disk structures we observe in galaxies. The rotation prevents additional compression while gravity maintains overall binding. Breaking through this barrier requires special mechanisms. Gas must transfer angular momentum to other components or radiate energy away through cooling processes. This barrier explains why galactic disks have minimum thickness limits and why stars form in specific patterns rather than collapsing directly into the central regions. Gas clouds don't collapse quietly. When different regions collide during the compression process, they create shock waves that dramatically heat the material. These collisions occur throughout the collapsing cloud. Faster moving gas rams into slower regions, converting motion energy into thermal energy. Temperatures spike to millions of degrees. Hot gas cannot collapse further. The increased thermal pressure pushes outward with enormous force, temporarily halting the gravitational compression process. This heating phase can last for hundreds of millions of years. During this period, star formation stops completely while the cloud struggles to cool down. The shock heating process explains why galaxy formation proceeds in stops and starts rather than smooth, continuous collapse. Hot gas must cool before collapse can resume. Fortunately, the universe provides efficient cooling mechanisms that remove thermal energy from heated clouds. Atomic collisions within the gas produce radiation that escapes into space. This radiative cooling steadily removes heat energy from the cloud interior. As temperature drops, thermal pressure weakens. Gravity regains dominance and collapse resumes. The cloud begins shrinking again toward its final configuration. Different elements cool at different rates. Hydrogen and helium require millions of years to cool effectively. Heavier elements cool much more rapidly. This cooling race determines the timeline of galaxy formation and explains why metal-rich regions form stars more efficiently than primitive gas clouds. Material in collapsing clouds must lose angular momentum to reach the central regions. Without this transfer mechanism, everything would remain stuck in wide orbits. Gravitational torques provide the solution. Non-uniform mass distributions create twisting forces that redistribute angular momentum throughout the cloud. Dense clumps and spiral patterns act as momentum transfer agents. They extract angular momentum from inner regions and transport it to outer areas. This process allows material to spiral inward while conserving the total angular momentum of the system. Inner gas loses rotation and falls toward the center. The efficiency of this transport mechanism determines how quickly disks form and how much material accumulates in galactic centers versus outer regions. Newly formed galactic disks don't remain smooth and featureless. Instabilities develop that organize matter into spiral patterns. These instabilities create traveling waves of compressed material. The waves move through the disk at speeds different from the orbital velocities of individual particles. Material flows into these compression zones, becomes temporarily concentrated, then flows out again. The wave pattern persists while individual particles cycle through it. This process transports material efficiently from outer regions toward the galactic center. It also triggers enhanced star formation in the compressed zones. Spiral density waves transform smooth disks into the structured galaxies we observe throughout the universe. Star formation requires gas to collapse to extremely high densities, but rotation creates outward forces that oppose this final compression. Centrifugal support prevents gas from reaching the critical densities needed for nuclear ignition. The spinning motion keeps material spread out in disk configurations. This delay mechanism explains why disk galaxies form stars gradually over billions of years rather than converting all their gas immediately into stellar populations. The process creates a cosmic traffic jam. Gas piles up in rotating configurations, waiting for opportunities to lose enough angular momentum for star formation. Only through complex feedback mechanisms can material eventually overcome centrifugal support and collapse into the dense cores that become new stars. Despite rotational barriers, some material does reach galactic centers. This central accumulation creates the dense nuclear regions found in most galaxies. Angular momentum loss mechanisms gradually feed material inward. Gravitational interactions, magnetic fields, and turbulence all contribute to this inward flow. The central mass concentration grows steadily over cosmic time. Eventually, it becomes massive enough to influence the dynamics of the entire galactic disk. Our galaxy's central black hole contains roughly 4 million solar masses concentrated into a region smaller than our solar system. This represents the end result of billions of years of gradual accumulation. The formation of these dense cores marks the final stage of the gravitational collapse process that transforms gas clouds into mature galactic systems. The first generation of stars dramatically alters conditions throughout their host galaxies. These massive, hot stars pump enormous amounts of energy into their surroundings. Stellar radiation heats nearby gas to thousands of degrees. Stellar winds blast material away from star-forming regions. Supernova explosions inject additional energy and heavy elements. This feedback process regulates future star formation. Heated gas cannot collapse easily into new stars. The energy input from existing stars controls the pace of galactic evolution. The feedback also enriches the gas with heavy elements created in stellar cores. This chemical evolution gradually changes the properties of subsequent stellar generations. Through these feedback mechanisms, early stars become architects that shape the structure and evolution of their entire galactic communities. Gas behaves like a crowded highway during rush hour. Individual particles constantly bump into their neighbors as the cloud collapses. Each collision transfers energy and momentum between particles. These collisions create friction within the gas. Unlike empty space, gas-filled regions experience internal resistance as material tries to move past itself. Every collision removes energy from the system. The particles lose speed with each impact, causing the overall gas motion to slow down gradually. This energy loss allows gravity to pull the gas inward more effectively. Scientists call this process dissipation, the conversion of motion energy into heat through particle interactions. The constant bumping and grinding creates the friction necessary for gas to spiral toward galactic centers. This collision mechanism explains why gas settles into thin disks much more efficiently than other galactic components. Stars live in a completely different universe than gas particles. Despite containing hundreds of billions of stars, galaxies provide so much empty space that stellar collisions almost never occur. The distances between stars dwarf their actual sizes. Our nearest stellar neighbor sits roughly 25 trillion miles away. Even during galactic collisions, stars pass through the chaos without touching. Stars interact only through gravitational attraction. They feel each other's gravity across vast distances but maintain their separate orbits. No friction occurs between stellar populations. This creates what astronomers call a collisionless system, a gravitational dance where participants never make physical contact. Stars respond only to the combined gravitational field of all their neighbors. The lack of stellar collisions means stars cannot lose energy through friction like gas particles do, fundamentally changing how stellar populations behave during galactic evolution. Angular momentum behaves differently in gas clouds versus stellar populations. This difference determines which components settle into thin disks and which remain puffy. Gas experiences internal friction through particle collisions. This friction removes angular momentum from individual gas parcels, allowing them to spiral inward toward galactic centers. The energy loss mechanism works continuously. Stars cannot lose angular momentum through collisions because they don't collide. Without energy dissipation, stellar orbits remain stable at their original distances from galactic centers. The result is selective settling. Gas forms thin disks through angular momentum loss. Stars maintain broader distributions because they retain their original orbital energy. This fundamental difference explains why galaxies develop layered structures with thin gas disks embedded within thicker stellar distributions. Different galactic components reach equilibrium on vastly different timescales. This timing difference controls the sequence of disk formation processes. Gas achieves equilibrium rapidly through frequent particle collisions. The constant interactions quickly redistribute energy and establish stable temperature and density patterns throughout gas clouds. Stars require much longer to reach equilibrium states. Gravitational interactions between stars happen slowly because the forces act across enormous distances. Stellar relaxation takes hundreds of times longer than gas relaxation. Our galaxy demonstrates this timing difference perfectly. The gas disk reached its current configuration within 1 billion years of formation. The stellar components still haven't fully relaxed after 10 billion years of evolution. This speed difference allows gas to form organized disk structures while stars continue slowly adjusting their distributions. Hot gas generates internal pressure that resists gravitational compression. This thermal support mechanism determines how thin galactic disks can become. Gas temperature creates outward pressure through particle motion. Faster-moving particles push against their neighbors with greater force. This thermal pressure opposes gravitational attraction. The balance between thermal pressure and gravity determines the final thickness of gas disks. Higher temperatures produce thicker disks. Cooler gas settles into thinner configurations. Cooling mechanisms gradually reduce gas temperatures over cosmic time. As thermal support weakens, gas can settle into progressively thinner layers. This creates the ultra-thin gas disks observed in mature galaxies. Without thermal pressure, gas would collapse completely into galactic centers rather than forming the stable disk structures that enable star formation. Stellar systems operate under completely different rules than gas systems. The absence of physical collisions creates unique dynamical behavior that preserves orbital structures. Individual stars move through space without exchanging energy with their neighbors. Gravitational interactions occur, but they conserve the total energy of stellar orbits rather than dissipating it. This energy conservation means stellar distributions remain stable over cosmic time, unlike gas, which can lose energy and spiral inward. Stars maintain their original orbital configurations indefinitely. The preservation of stellar orbital energy explains why elliptical galaxies, composed primarily of stars, retain their round shapes. Without energy dissipation mechanisms, stellar systems cannot flatten into disks. Only when external forces disrupt galactic systems do stellar orbits change significantly from their initial configurations. Magnetic fields thread through galactic gas like invisible highways for angular momentum transport. These fields provide mechanisms for moving rotational energy from inner regions to outer zones. gas particles carry electric charges that interact with magnetic fields. When charged particles move, they create currents that couple to the magnetic field lines threading the gas. This magnetic coupling enables long-distance transport of angular momentum. Material can lose rotation in inner regions, while outer zones gain angular momentum through magnetic field connections. The process operates much more efficiently than gravitational interactions alone. Magnetic fields can transport angular momentum across entire galactic disks within relatively short time periods. Without magnetic angular momentum transport, gas would remain locked in wide orbits and never reach the central regions where most star formation occurs. Turbulence creates a special type of friction within galactic gas. Random, chaotic motions generate effective viscosity that enhances energy dissipation beyond simple particle collisions. Gas motions become turbulent when different regions move at different velocities. Shear forces between fast and slow zones create swirling, chaotic patterns that mix the material. These turbulent motions transfer energy from large-scale flows to small-scale random motion. The randomized motion then dissipates as heat through microscopic processes. Turbulent viscosity works thousands of times more effectively than molecular viscosity alone. This enhanced friction mechanism accelerates the disk formation process significantly. The chaotic nature of turbulence ensures that gas loses angular momentum and energy much faster than would occur through orderly particle interactions. Stars don't just shine. They blast material into space at tremendous velocities. These stellar winds carry enormous amounts of energy that heat surrounding gas to extreme temperatures. Massive stars produce particularly powerful winds. Material streaming from stellar surfaces travels at speeds of thousands of kilometers per second, creating shock waves when it collides with ambient gas. The heating effect is dramatic. Cool gas suitable for star formation gets heated to temperatures that prevent further collapse. This creates a feedback loop that regulates the pace of stellar birth. Hot gas expands and creates cavities around young star clusters. These heated regions can persist for millions of years, fundamentally altering the structure of galactic disks. Stellar feedback prevents runaway star formation and helps maintain the delicate balance that preserves long-lived disk structures. Galaxy formation doesn't happen all at once. The process occurs in two distinct phases that build galactic components in a specific sequence. Gas settles into disk configurations first, through energy dissipation and angular momentum transport. Gas rapidly forms thin, rotating structures within dark matter halos. Star formation begins only after gas disks become established. The organized gas provides the stable environment necessary for gravitational collapse into individual stellar objects. This sequential process explains why disk galaxies show layered structures. The gas disk forms the foundation, while stellar populations build up gradually through billions of years of star formation. Our galaxy demonstrates this two-phase assembly perfectly. The underlying gas disk established the architectural framework that continues to guide star formation 10 billion years after the initial collapse began. Spiral arms aren't made of specific stars. They're traveling waves of compression that move through galactic disks like traffic jams on a cosmic highway. This concept revolutionized our understanding of galactic structure. Scientists call it density wave theory, the idea that spiral patterns represent regions of enhanced density rather than permanent stellar arrangements. The waves move at their own speed through the disk. Individual stars drift into spiral regions, spend time in the compressed zones, then drift out again. The spiral pattern persists while stellar populations flow through it. Think of a traffic jam moving backward along a highway. Cars enter the jam from behind, slow down in the congested area, then exit ahead. The jam maintains its shape while different cars pass through it. This wave mechanism solves the puzzle of how spiral patterns survive for billions of years despite galactic rotation that should destroy fixed structures. Galactic disks create a fundamental problem for spiral arm persistence. Different regions rotate at different speeds, which should quickly destroy any fixed spiral pattern. If spiral arms were permanent features rotating with the stars, they would wind up like thread on a spool. Inner regions rotate faster than outer zones, causing spiral patterns to become increasingly tight. Mathematical calculations show this winding process works devastatingly fast. Any fixed spiral structure should completely wrap up and disappear within just 2 or 3 galactic rotations. Our galaxy has completed roughly 50 rotations since its formation. By simple rotation logic, spiral arms should have vanished 47 rotations ago. Yet spiral patterns persist throughout the universe in galaxies of all ages, proving that spiral arms cannot be permanent, rotating features but must represent some other type of structure entirely. Certain stellar orbits synchronize perfectly with spiral wave patterns. This orbital matching creates resonance zones where waves and stellar motion coordinate their timing. Resonance occurs when stellar orbital periods match spiral pattern periods in simple mathematical ratios. A star might complete exactly 3 orbits while the spiral pattern completes 2 rotations. These synchronized regions provide stability anchors for spiral patterns. Stars in resonance zones reinforce the wave structure rather than disrupting it through chaotic motion. Our galaxy contains multiple resonance zones at different distances from the center. Each zone helps maintain spiral coherence through gravitational coupling between stellar orbits and density waves. The resonance mechanism explains why spiral patterns maintain consistent shapes across cosmic time despite the destructive effects of differential rotation. Spiral arms act like cosmic snowplows that compress gas as the density waves sweep through galactic disks. This compression triggers the formation of new stellar generations. Gas flowing into spiral regions encounters the moving density wave head-on. The collision creates shock waves. Sudden pressure increases that compress the gas to much higher densities. Compressed gas becomes unstable and begins collapsing under its own gravity. This process initiates star formation on massive scales within spiral arm regions. The shock compression mechanism explains why spiral arms appear so bright and prominent in photographs. They glow with the light of countless newly formed stars born from the compression process. This star formation factory operates continuously as gas flows through successive spiral regions, creating the brilliant stellar highways that define galactic architecture. Spiral arms shine brilliantly not because they contain more stars, but because they contain the brightest types of stars in the galaxy. Newly formed stars include massive, hot blue giants that burn with incredible intensity. These stellar powerhouses outshine dozens of ordinary stars like our Sun. Hot blue stars have extremely short lifespans, only 10 million years before exploding as supernovae. They die before they can drift far from their spiral arm birthplaces. This creates a visual effect where spiral arms appear packed with bright stars. In reality, the total stellar density stays roughly constant throughout galactic disks. The brilliant blue light from young massive stars traces the spiral pattern, making these density wave structures visible across intergalactic distances. Spiral patterns rotate at completely different speeds than the stars within galactic disks. This speed difference enables long-term pattern survival. The spiral pattern moves more slowly than most stellar orbits. Stars repeatedly catch up to spiral arms from behind, pass through the density zones, and exit ahead. Scientists call this the pattern speed, the rotational velocity of the spiral wave structure itself. This speed stays constant while stellar orbital velocities vary with distance. The speed difference means spiral arms continuously receive fresh material as stars flow through them. The pattern doesn't depend on keeping the same stars in place indefinitely. This velocity decoupling solves the winding problem that would destroy fixed spiral structures through differential rotation effects. Many galaxies contain elongated central structures that generate and maintain their spiral patterns. These galactic bars act like cosmic stirring rods that create density waves. Our galaxy possesses such a central bar, a region where stars orbit in elongated patterns rather than circular paths. This bar rotates as a rigid structure through the galactic center. The rotating bar creates gravitational disturbances that propagate outward through the galactic disk. These disturbances organize into the spiral density wave patterns we observe. Computer simulations demonstrate how bars naturally generate spiral arms. The bar's gravitational field creates periodic compression zones that spiral outward from the central regions. This bar-driven mechanism provides the energy source needed to maintain spiral patterns against the dissipative forces that would otherwise cause them to fade away. Galactic disks can generate spiral patterns through their own gravity without requiring external driving forces. This self-organization process emerges from disk gravitational instabilities. Dense regions in galactic disks create stronger gravitational fields that attract surrounding material. This attraction causes matter to flow toward the dense zones, making them even denser. The process creates a feedback loop where density enhancements grow stronger over time. Eventually, these density perturbations organize into spiral wave patterns. The disk's own rotation shapes these gravitational instabilities into spiral forms. Material flowing toward dense regions gets deflected by rotational forces into curved trajectories. Self-gravity provides an alternative explanation for spiral structure that doesn't require central bars or external disturbances to maintain the patterns. Close encounters between galaxies create gravitational tides that can induce spiral structure formation in previously smooth galactic disks. When galaxies pass near each other, their gravitational fields interact across the intervening space. These tidal forces stretch and compress galactic material in specific patterns. The tidal disturbances often organize into spiral configurations that persist long after the galaxies separate. A single close encounter can trigger spiral formation that lasts for billions of years. Our galaxy shows evidence of past tidal interactions with smaller companion galaxies. These encounters may have contributed to our current spiral structure. Tidal triggering explains why some galaxies develop spiral patterns suddenly rather than maintaining them continuously from formation. Galaxy rotation patterns often correlate with their orbital motion through larger cosmic structures. This spin-orbit coupling influences spiral arm development and maintenance. 2. Galaxies moving through galaxy clusters experience environmental effects that can either enhance or suppress spiral structure formation. The direction of motion relative to rotation affects stability. When galactic rotation aligns with orbital motion through cosmic structures, Spiral patterns become more stable and long-lived. Misaligned systems experience more disruption. Our local group shows examples of this coupling effect. Galaxy orientations and rotation patterns reflect their orbital relationships within the group. This cosmic scale coupling demonstrates how galactic structure connects to motion through the larger universe, linking spiral formation to cosmological dynamics. Spiral arms cannot persist indefinitely. Various energy dissipation mechanisms gradually weaken spiral patterns until they fade away entirely. Star formation within spiral arms removes gas from the disk through stellar winds and supernova explosions. This mass loss weakens the gravitational fields that maintain density waves. Viscous effects within galactic gas create friction that dampens spiral wave motion. The patterns lose energy and amplitude over cosmic time through these dissipative processes. Old galaxies often show weaker spiral structure than younger systems. The gradual energy loss explains why ancient galaxies tend toward smoother, less structured appearances. Understanding spiral dissolution helps astronomers predict how galactic structure will evolve over the remaining lifetime of the universe. Not all gas clouds start their cosmic journey with the same rotational properties. This initial difference determines whether galaxies become flat disks or round balls of stars. Clouds with significant rotation evolve into spiral galaxies through the angular momentum conservation process we've explored. The spinning motion flattens these systems into thin disk structures. But clouds with minimal initial rotation follow a completely different evolutionary path. Without strong rotational forces to prevent collapse, gravity pulls material inward equally from all directions. These slowly rotating systems become elliptical galaxies, round or oval collections of stars with no disk structure. They represent roughly 30% of all large galaxies in the universe. The amount of initial spin in primordial gas clouds acts as a cosmic switch that determines the final architectural destiny of galactic systems. Galaxy collisions completely destroy the delicate disk structures that took billions of years to form. These violent encounters scramble stellar orbits and eliminate organized rotation patterns. When two spiral galaxies collide, their gravitational fields interact chaotically. Stars get flung into random trajectories that bear no resemblance to their original orderly disk orbits. The collision process takes several billion years to complete. During this time, the organized rotation that maintained disk structure gets converted into random stellar motion. Computer simulations reveal the transformation process in detail. Two beautiful spiral galaxies merge and emerge as a single elliptical system with no remaining disk architecture. Our galaxy will experience this fate when it collides with Andromeda in approximately 4 billion years, creating a new elliptical galaxy from two current disk systems. Sudden changes in gravitational fields can instantly destroy the careful orbital organization that maintains galactic disk structures. Scientists call this process violent relaxation. During galaxy mergers, the combined gravitational field changes rapidly and unpredictably. Stars that once followed stable circular orbits suddenly experience completely altered gravitational environments. These abrupt gravitational changes scatter stellar velocities in random directions. The orderly rotation that characterizes disk galaxies becomes chaotic motion with no preferred direction. The relaxation process happens much faster than normal gravitational evolution. What would normally take hundreds of billions of years occurs within just a few billion years during major mergers. This rapid scrambling mechanism explains how disk galaxies can transform into elliptical systems within cosmologically short time periods. Galaxies cannot maintain disk structures without a continuous supply of gas to fuel ongoing star formation and replace material lost to various processes. Efficient star formation converts gas into stars faster than new material can flow into galactic systems. The stellar conversion process depletes the rotating gas reservoirs that maintain thin disk architectures. Stellar feedback mechanisms also remove gas from galaxies. Supernovae and stellar winds blast material out of galactic gravitational wells, preventing it from contributing to continued disk formation. Without gas replenishment, existing disk structures gradually fade as stars evolve and die. The thin gas layers that define disk architecture disappear entirely. Gas-poor galaxies naturally evolve toward elliptical configurations because they lack the material necessary to maintain or rebuild flattened structures. Stars in elliptical galaxies move in completely different patterns than stars in disk galaxies. Random motion dominates over organized rotation in these spherical systems. Scientists measure this random motion through velocity dispersion, the range of different speeds and directions exhibited by stellar populations. High dispersion means chaotic motion. Elliptical galaxies show extremely high velocity dispersions. Stars move in all directions with a wide range of speeds. This random motion prevents the formation of thin disk structures. In contrast, disk galaxies maintain low velocity dispersions. Most stars follow similar circular orbits in the same direction, creating the organized motion necessary for flat architectures. When velocity dispersion exceeds rotational velocity, galaxies cannot maintain disk structures and naturally adopt spherical configurations instead. Galaxies living in crowded cosmic environments face destructive forces that gradually strip away their disk structures and transform their shapes. Galaxy clusters contain hundreds of individual galaxies packed into relatively small cosmic volumes. These dense environments create harsh conditions for maintaining delicate disk architectures. Gravitational interactions between neighboring galaxies distort and heat stellar distributions. Close encounters inject random motion into previously ordered stellar populations. The cluster environment also removes gas through various stripping mechanisms. Without gas to maintain disk structures, galaxies gradually transition toward elliptical configurations. Observations confirm this environmental effect. Galaxy clusters contain much higher fractions of elliptical galaxies than isolated regions of space. Hot gas filling galaxy clusters acts like a cosmic headwind that strips material from galaxies moving through these dense environments. When galaxies move rapidly through cluster gas, they experience ram pressure, resistance from the hot intergalactic medium. This pressure can overcome galactic gravity and remove loosely bound material. Gas in galactic disks gets stripped away first because it's more easily removed than tightly bound stellar components. The process selectively destroys the gas layers that define disk architecture. Ram pressure stripping operates most efficiently on galaxies moving at high speeds through dense cluster cores. These galaxies lose their gas content and disk structure within several 100 million years. The stripped galaxies transform into gas-poor elliptical systems that can no longer maintain their original flat architectures. Repeated close encounters with neighboring galaxies create cumulative damage that eventually destroys disk structures through a process called gravitational harassment. Unlike major mergers that completely destroy galaxies in single events, Harassment involves many smaller interactions that gradually heat and disrupt stellar distributions. Each close encounter adds random motion to stellar orbits. Over cosmic time, these small perturbations accumulate and eventually overwhelm the organized rotation that maintains disk structures. The harassment process works most effectively in dense environments where galaxies frequently encounter their neighbors. Galaxy clusters provide ideal conditions for this gradual disruption mechanism. Harassment explains why many elliptical galaxies show signs of past disk structures that were slowly destroyed through repeated gravitational disturbances rather than catastrophic collisions. Gravitational interactions within galaxy clusters gradually separate stars by mass, concentrating heavier objects toward cluster centers while lighter stars migrate outward. This mass segregation process operates through repeated gravitational encounters between individual stars during galaxy interactions. More massive stars sink toward gravitational potential wells. Heavy stars tend to follow more circular, organized orbits that maintain disk-like distributions. Light stars develop more random, elliptical orbits that contribute to spherical galaxy shapes. The segregation process removes the most massive stars from galactic disks, weakening the gravitational structure that maintains flat architectures. Disks become less stable without their heaviest stellar components. Over cosmic time, mass segregation contributes to the transformation of disk galaxies into elliptical systems by selectively removing the stellar populations most important for disk stability. Astronomers discovered a fundamental relationship between cosmic environment density and the types of galaxies found in different regions of space. Dense environments like galaxy cluster cores contain predominantly elliptical galaxies with little disk structure. Sparse regions show mostly spiral galaxies with prominent disk architectures. This morphology-density relation demonstrates how environment shapes galactic evolution. Crowded cosmic neighborhoods transform disk galaxies into elliptical systems through multiple destructive mechanisms. The relationship appears universal across different cosmic epochs and environments. Higher density consistently correlates with higher elliptical galaxy fractions throughout the observable universe. Understanding this environmental influence helps astronomers predict how galaxy populations will evolve as cosmic structure continues developing and environments become denser over time. Every galaxy sits inside a massive, invisible bubble that extends far beyond its visible boundaries. This dark matter halo provides the gravitational foundation that makes disk formation possible. The halo dwarfs the visible galaxy in both size and mass. While galactic disks span roughly 100,000 light-years, their dark matter halos extend over 1 million light-years into space. Unlike the flat disk structure of visible matter, dark matter halos maintain spherical shapes. They form round gravitational wells within which ordinary matter can settle into organized disk configurations. The halo contains roughly 10 times more mass than all the visible stars and gas combined. This invisible component dominates the gravitational environment that shapes galactic architecture. Without dark matter halos providing this spherical framework, ordinary matter could never achieve the stable disk structures that characterize most galaxies throughout the universe. Astronomers measuring stellar velocities across galactic disks discovered something impossible according to visible matter alone. Stars in outer regions move much faster than they should. Simple physics predicts that orbital velocities should decrease with distance from galactic centers, just like planets orbiting farther from the Sun move more slowly than inner planets. Instead, galactic rotation curves remain surprisingly flat. Stars maintain nearly constant velocities regardless of their distance from central regions. This contradicts expectations based on visible matter distributions. The flat rotation pattern requires additional invisible mass distributed throughout galactic volumes. Without this hidden matter, outer stars would fly away into intergalactic space. Dark matter provides the missing gravitational influence that keeps high-velocity outer stars gravitationally bound within galactic systems despite their tremendous orbital speeds. Dark matter behaves fundamentally differently from ordinary matter during galactic formation. While gas particles collide and interact, dark matter particles pass through each other without touching. This collisionless property prevents dark matter from losing energy through friction or other dissipative processes. Dark matter cannot cool down and settle into thin disk configurations. The inability to dissipate energy explains why dark matter maintains spherical distributions. Without energy loss mechanisms, dark matter particles retain their original random orbital motions. Collisionless dynamics also means dark matter cannot form the complex structures that characterize ordinary matter. No dark matter stars, planets, or organized disk systems can exist. This fundamental difference between matter types creates the layered structure observed in galaxies. Spherical dark matter halos containing flattened disks of ordinary matter. Computer simulations reveal how dark matter distributes itself within galactic halos. The density pattern follows specific mathematical relationships that appear universal across galaxy types. Scientists call this pattern the NFW profile, a mathematical description of how dark matter density changes from galactic centers to outer edges. Density peaks at intermediate distances rather than at the very center. The central regions show lower dark matter densities than expected from simple gravitational collapse models. This creates what astronomers call cuspy versus core density profiles. Real galaxies often show even flatter central density distributions than pure dark matter simulations predict. The interaction between ordinary and dark matter during galaxy formation modifies the final density patterns. Understanding these density profiles helps astronomers map the invisible architecture that supports visible galactic structures throughout cosmic space. Ordinary matter and dark matter can exchange angular momentum during galaxy formation despite their different physical properties. This transfer process shapes the final structure of both components. Gravitational interactions provide the coupling mechanism between matter types. Dense clumps of ordinary matter create gravitational disturbances that affect nearby dark matter particle orbits. The exchange typically transfers angular momentum from ordinary matter to dark matter. This allows gas to lose rotation and settle into disk configurations while dark matter retains spherical distributions. The efficiency of this transfer process determines how much material can reach central galactic regions. More efficient transfer leads to more concentrated galactic cores. Angular momentum exchange explains how dark matter halos can support disk formation while maintaining their own spherical architecture throughout the process. Dark matter halos create gravitational boundaries that determine the maximum possible size of galactic disks. Material beyond these boundaries cannot remain gravitationally bound to galactic systems. The tidal radius marks the distance where external gravitational forces become comparable to galactic gravity. Material beyond this point gets stripped away by neighboring cosmic structures. This gravitational limit explains why galactic disks don't grow indefinitely despite continuous material accretion from surrounding space. The halo's tidal boundary sets firm size constraints. Different halo masses create different tidal boundaries. More massive halos can support larger disk structures, while smaller halos limit disk growth to more compact configurations. The tidal radius effect provides a natural explanation for the observed correlation between dark matter halo masses and the sizes of their embedded galactic disks. Dark matter halos aren't smooth, uniform structures. They contain numerous smaller dark matter clumps called subalos that can disrupt the orderly motion of galactic disks. These subalos represent the remnants of smaller dark matter structures that merged with larger halos during cosmic structure formation. They survive as distinct entities within the larger gravitational environment. When subalos pass through galactic disks, they create gravitational disturbances that heat stellar populations and inject random motion into previously organized orbital systems. The frequency of subalo encounters determines how much disruption galactic disks experience over cosmic time. Halos with many subalos create more chaotic environments for disk maintenance. Subhalo interactions explain some of the thickening and heating observed in old galactic disk populations compared to younger, more organized stellar distributions. Moving objects within dark matter halos experience a drag force that slows their motion despite the collisionless nature of dark matter. This process operates through purely gravitational interactions. When massive objects move through dark matter, they gravitationally attract nearby dark matter particles. This creates a wake of enhanced density trailing behind the moving object. The density wake exerts gravitational forces that oppose the object's motion, creating an effective friction force. The object loses kinetic energy and spirals inward toward the halo center. Dynamical friction affects satellite galaxies, massive star clusters, and other dense objects moving through galactic halos. The process can cause these objects to merge with central galaxies over time. This gravitational friction mechanism helps explain the orbital decay and eventual merger of satellite systems within larger galactic environments. Dark matter halos possess different amounts of rotation that strongly influence how efficiently they can form galactic disk structures. This rotation parameter affects the final architecture of embedded galaxies. Halos with higher spin parameters, more initial rotation, provide better environments for disk formation. The rotational support helps ordinary matter settle into stable disk configurations. Low-spin halos create more spherical gravitational wells that favor the formation of elliptical galaxies rather than disk systems. The lack of rotational support prevents efficient disk assembly. The spin parameter distribution in dark matter halos explains the observed mix of galaxy types throughout the universe. Different rotation amounts naturally produce different galactic architectures. Understanding halo spin properties helps astronomers predict which cosmic environments will produce disk galaxies versus elliptical systems during structure formation. Hot gas trapped within dark matter halos gradually cools and flows inward to fuel ongoing galactic disk growth. This cooling process operates continuously throughout cosmic history. Gas initially heated during halo formation must radiate away thermal energy before it can participate in disk structures. Cooling mechanisms remove heat energy through various radiation processes. As gas cools, it loses pressure support and begins flowing toward the gravitational center of the dark matter halo. This creates steady accretion streams that feed growing galactic disks. The cooling efficiency determines how rapidly galaxies can grow through gas accretion. More efficient cooling leads to faster disk assembly and more massive final systems. Cooling flows provide the material supply necessary for sustained star formation and continued galactic evolution within dark matter gravitational wells. Dark matter provides the fundamental framework for all cosmic structure formation through a process that builds large systems from smaller components over cosmic time. Dark matter collapses first because it responds only to gravity without pressure support. This creates the gravitational wells necessary for subsequent ordinary matter assembly. Small dark matter halos form earliest in cosmic history. These systems gradually merge and grow into the massive halos that host large galaxies in the modern universe. Ordinary matter follows the dark matter template, falling into established gravitational wells and organizing into the galactic structures we observe today. This hierarchical formation sequence explains why galactic properties correlate with dark matter halo properties. The invisible framework determines the architecture of visible cosmic structures. Galaxies don't spring into existence fully formed. They grow through a cosmic construction process that builds large systems from smaller building blocks over billions of years. This bottom-up assembly process dominates cosmic structure formation. Scientists call it hierarchical formation, the systematic growth of massive structures through merger and accretion of smaller components. Small galaxies form first in cosmic history. These early systems contain fewer stars and simpler structures than modern galactic giants. Over time, gravity pulls these smaller systems together into increasingly massive assemblages. Each merger event adds mass, complexity, and new structural features to the growing galactic system. The process continues throughout cosmic history as larger systems continue absorbing smaller neighbors. Our galaxy shows clear evidence of this hierarchical growth through the remnants of past merger events still visible in its stellar populations and structural features. Galactic disks require continuous material input to maintain their structure and fuel ongoing star formation. This fresh material arrives from the surrounding cosmic environment through various accretion processes. Cold gas streams flow along cosmic web filaments directly into galactic halos. These pristine gas supplies provide the raw material necessary for continued disk growth and stellar production. The accretion process operates gradually over cosmic time. Unlike dramatic merger events, gas accretion proceeds quietly and steadily without disrupting existing galactic structures. Steady accretion explains how disk galaxies maintain their flat architectures despite billions of years of star formation that should deplete their gas reservoirs. The external supply replenishes consumed material. Without continuous gas accretion, galactic disks would exhaust their fuel supplies and cease forming new stellar populations within just a few billion years. The pace at which galaxies convert gas into stars determines their evolutionary pathway and final structural configuration. Different consumption rates produce different galactic destinies. Rapid star formation quickly exhausts gas supplies and halts further disk growth. These starbursting systems evolve into gas-poor elliptical galaxies with no remaining fuel for continued structural development. Slow, steady star formation preserves gas reservoirs over extended periods. These galaxies maintain disk structures and continue evolving through sustained stellar production and chemical enrichment. The star formation efficiency acts like a cosmic throttle that controls how rapidly galaxies consume their structural building materials. Higher efficiency leads to faster evolution and earlier structural maturation. Understanding star formation rates helps astronomers predict which galaxies will maintain disk architectures versus those destined to become spherical elliptical systems. When galaxies of similar mass collide, the encounter completely transforms both systems into something entirely different. These major merger events rank among the most destructive processes in cosmic evolution. The gravitational chaos during major mergers scrambles stellar orbits and destroys organized disk structures. Both galaxies lose their original architectures and emerge as a single elliptical system. Computer simulations reveal the transformation process in detail. Two beautiful spiral galaxies approach, interact gravitationally, and eventually merge into one large elliptical galaxy with no remaining disk features. The merger process typically requires several billion years to complete. During this time, intense star formation consumes remaining gas supplies and creates the old stellar populations characteristic of elliptical galaxies. Major mergers represent evolutionary dead ends that terminate disk galaxy evolution and produce the largest elliptical systems observed throughout the universe. Not all galactic encounters result in structural destruction. When large galaxies absorb much smaller companions, the process can enhance rather than eliminate disk structures. Minor mergers involve mass ratios of roughly 10 to 1 or greater. The smaller galaxy lacks sufficient mass to disrupt the larger system's gravitational organization significantly. The absorption process adds stellar mass to galactic disks without destroying their fundamental architecture. The accreted material settles into existing orbital patterns and strengthens disk gravitational binding. Many disk galaxies show evidence of past minor merger events through stellar streams and other structural signatures. These encounters represent growth opportunities rather than destructive catastrophes. Minor mergers explain how some disk galaxies achieve massive sizes while maintaining their flat structures throughout billions of years of cosmic evolution. Galaxies undergo structural changes even without external influences. Internal gravitational instabilities develop over time that reshape galactic architecture through purely internal processes. Bar instabilities represent the most common internal evolution mechanism. Central regions of disk galaxies can spontaneously develop elongated stellar distributions that rotate as rigid structures. These galactic bars dramatically alter gas flow patterns within disks. Material gets funneled towards central regions, triggering enhanced star formation and building up central mass concentrations. Spiral density waves also contribute to internal evolution by redistributing material and angular momentum throughout galactic disks. These waves transport mass inward while spreading angular momentum outward. Secular evolution demonstrates how galaxies can transform their structures through internal processes alone, independent of environmental influences or merger events. Galaxies living in different cosmic neighborhoods experience different evolutionary pressures that shape their final structural configurations. Environment plays a crucial role in determining galactic destiny. Dense galaxy clusters create hostile conditions for maintaining delicate disk structures. High-speed encounters, tidal forces, and gas-stripping mechanisms gradually transform disk galaxies into elliptical systems. The cluster environment removes star-forming gas through various physical processes. Without gas to fuel ongoing disk maintenance, galaxies naturally transition toward elliptical configurations. Isolated galaxies in sparse environments face fewer destructive influences and can maintain disk structures over much longer periods. These systems continue evolving through internal processes and minor mergers. The correlation between environment and galaxy type demonstrates how cosmic setting influences evolutionary outcomes across billions of years of galactic development. Astronomers can observe galaxy evolution directly by studying systems at different cosmic distances. Light travel creates a natural time machine for exploring galactic history. Distant galaxies appear as they existed billions of years ago when their light began its journey to Earth. These observations reveal how galaxy populations have changed over cosmic time. Early universe galaxy populations show dramatically different characteristics than modern systems. Irregular, chaotic structures dominated cosmic history, while organized disk galaxies remained relatively rare. The fraction of disk galaxies increases steadily from early times to the present epoch. This demonstrates that organized structures develop gradually through cosmic evolution rather than forming immediately. Redshift studies provide direct evidence for the hierarchical formation paradigm by showing how galactic complexity increases systematically over cosmic time. Many galaxies undergo dramatic transitions where active star formation suddenly ceases and disk structures fade into smooth, featureless distributions. This process fundamentally alters galactic character. Scientists call this transformation quenching, the rapid termination of star formation that converts gas-rich spiral galaxies into gas-poor lenticular systems. The change happens relatively quickly in cosmic terms. Various mechanisms can trigger quenching events. Environmental effects, internal feedback processes, or external gas removal can all shut down the star formation that maintains disk structures. Quenched galaxies lose their spiral patterns and develop smooth stellar distributions. They retain disk-like shapes, but lack the active star formation regions that create spiral arm features. The quenching process represents an intermediate evolutionary stage between active spiral galaxies and passive elliptical systems in the cosmic hierarchy. Our galaxy's disk structure will not persist indefinitely. Astronomers have identified a future collision that will completely transform the Milky Way's architecture within the next 5 billion years. The Andromeda Galaxy approaches our system at tremendous speed. Current measurements indicate an inevitable collision that will merge both galaxies into a single massive elliptical system. Computer simulations predict the encounter's outcome in detail. The gravitational interaction will scramble stellar orbits, destroy both disk structures, and create a new elliptical galaxy astronomers call Milkomeda. The merger process will take roughly 4 billion years to complete. During this time, our solar system will likely survive but end up in a completely different galactic environment. This future transformation demonstrates that even stable disk structures represent temporary phases in cosmic evolution rather than permanent galactic configurations.